So the purpose of this video is to preview a lab that we are going to do in class called the Kinetics of Crystal Violet. Kinetics of Crystal Violet. So crystal violet, as I have described before, is a compound. It's a dye, a biological dye that's used for a lot of different purposes, and it has this purplish violet color. The reaction that we're going to do is we're going to take crystal violet, which I've abbreviated with CV plus here, has a slightly positive charge, one positive, and we're going to react it with sodium hydroxide, a strong base, NaOH. So the net ionic equation is going to be crystal violet plus hydroxide produces CVOH, the protonated form of crystal violet. When this happens, when OH reacts with crystal violet, the purple color disappears. The new molecule that's formed doesn't give off a purple color. So as you can see here, this time is from 0 to 600 seconds. We can see is here no NaOH has been added. Then once it's added, over time, you can tell the color is going to get less and less purple. All right? We're going to try to measure the rate law of this reaction. So what we know so far is the rate law, rate equals K times the concentration of Cv plus to the power of X, and the concentration times the concentration of OH minus to the power of Y. So this is what the rate law is. But our goal now is to figure out what is Y, what is X, and what is K by collecting our own data and then using our knowledge of kinetics to solve for those three variables. So we're going to figure out the order with respect to crystal violet. So in order to do that, we're going to change the concentration of crystal violet, and the concentration of hydroxide is going to stay constant. Just like the data we've looked at in our tables, one reactant has to stay constant while the other one changes. So we're going to do that here in our lab. In order to do this, we're going to use a tool called a spectrophotometer. Fancy, fancy word sounding, but it's really not that tricky. Meter means to measure. Photo means light. Okay? So we're basically, and spectro means spectrum. Okay? Different light, wavelengths. So we're going to basically measure light in different ways in order to figure out the kinetics of this equation. So the device that we're going to use looks exactly like this. The way this works, just to give you a quick overview, is you're going to take these small little plastic cuvettes. So again, the way this is pronounced is a cuvette, not cuvette, a cuvette. Okay? We fill up the cuvettes with some solution. Okay? In this case, it's going to be our crystal violet with sodium hydroxide. We then take the cuvette and we put it into this little hole. What happens then is the spectrophotometer shines light through the cuvette. Okay? And there's a little detector on this side, okay, that detects how much light is getting through. If we think about it very clearly, the more purple there is in this, okay, less light gets through. So for example, over here, when the dye looks like this, very little light's going to get through because it's very darkly colored. But over time, as the reaction occurs, more and more light is going to be able to go through the cuvette because some of that dye is becoming colorless. So over time, more light will get through. So don't worry about this data right here, okay? But what we're going to plot eventually is we're going to have, this is going to be connected to my computer, okay? This is what we're going to see on the computer screen. We're going to have time on the x-axis, and we're going to have absorbance on the y-axis. Absorbance is basically measuring how much light gets through. Higher absorbance means more light is getting through. Lower absorbance means less light is getting through. Okay? So, this is what it's going to look like. I just wanted to give you an overview of the equipment. The details you need to know about using the spectrophotometer. Remember, in the rate law, we need to change concentration. But the spectrophotometer doesn't measure concentration. It measures absorbance. So what we're going to need to use is something called Beer-Lambert's law. Beer-Lambert's law relates concentration and absorbance. And the equation for Beer-Lambert's law is A equals little a, B, C, just the alphabet. What do these things represent? C is concentration in molarity. Okay? B, this is the width of the cuvette, which is often called the path length. So in the cuvette here, how wide is it? How far does the light have to travel through? And this is going to be 1 centimeter, which is 10 millimeters. It's basically the same. That's pretty standard for cuvettes. A is called the molar absorptivity coefficient. Okay? And this is a number that's unique to every compound in the world. Just like every reaction has a rate constant that's unique for that reaction, every compound has a molar absorptivity coefficient that's unique to that compound. So I'll give you the molar absorptivity coefficient for crystal violet in the lab. A is then our absorbance. So what you can tell is if we know the absorbance, this is going to be equal to 1, this is a constant, we can then solve for concentration. We're basically just doing a conversion from absorbance to concentration. What you need to know is that this is called Beer-Lambert's law, and you need to know how to use it. So if you plug in a number for A, you can figure out concentration if you're given these two values. Okay? The computer will do that for us, luckily, and then our job will be to analyze the data. But before we analyze the data, we have to think about actually experimentally what's going to happen. So when you buy crystal violet, this is a bottle of crystal violet, CV+. It usually comes in a very, very concentrated form. It's usually in 250 micromolar. Okay? Micro, this prefix, is 10 to the negative 6th. Okay? 10 to the negative 6th molar. So what we need to do in most of these labs, though, is we're going to change the concentration to different concentrations. Each group is going to have a different concentration. Some might have 250, some might have 100, some might have 50. But how would we do that? This should be a little bit of review. Let's say you wanted to dilute the 250 micromolar stock solution, so where the stock is what's given to you. You wanted to dilute it to 10 micromolar. How do you do that? The equation that we need to do for dilutions, and this is a good formula to remember anytime you're dealing with concentrations, M1 V1 equals M2 V2. And we've covered this before. But just a reminder, 1s are like your initial concentrations, and 2s are what the final ones are going to be. So let's say we wanted to make 1 milliliter of 10 micromolar concentration. And we want to figure out how much of this stock are we going to need. Okay? Excuse me, let's make it 10 milliliters. So let's just plug in our numbers. Okay? Our starting concentration is 250 micromolar. So 250 micromolar. That's a U. Our V2, or V1, the volume that we need of this, we don't know yet. We're trying to figure it out. V2. Our new molarity, we want to be 10 micromolar. Okay? And our final volume, we want to make 10 milliliters of it. So there's the quick setup. So if we multiply this out, we would get 250 times V2 equals 100. Divide by both sides by 250. Okay? So volume 2 would be equal to 100 divided by 250 in terms of milliliters. So if you do the math for that, you get 0.4 milliliters. So what does that mean? Stop and think. This means that I'm going to need 0.4 milliliters of crystal violet. I'm trying to make 10 milliliters total. So here's like a graduated cylinder. Here's 0.4. This is my crystal violet. So what am I going to need to add to get up to 10 milliliters? I'm just going to add water. Okay? And to figure out exactly how much water, I would just subtract these. So 10 minus 0.4, 9.6 milliliters of water will be needed. Just think about it. It's like you have some really strong Kool-Aid, okay? You take a little bit of it and you add a bunch of water. That's going to make it less strong. It's going to lower the concentration. In this case, exactly from 250 down to 10. So here are 3 more problems. What I recommend that you do is you pause the video in a second to answer each of these. How would you dilute each of the following if you had a stock solution of 250? And let's say you want to make, well, for ease, you still want to make 10 milliliters of the dilute solution. So I would recommend pausing the video now, trying each of these 3, and then checking your answers by pressing play in a minute. So for 1, it'd be M1 V1 equals M2 V2. That's the equation you're going to use for every single one of these problems. Okay. So if I plug in my values, I'm starting with 250. I don't know V1. M2, I want to make it 25. I want to make 10 milliliters of it. So I get 250 equals 250 times V1. So V1, I would need, divide both sides by 250. I would need 1 milliliter of crystal violet. So to make 10 milliliters total, I would need 9 milliliters of H2O. Combine those into a graduated cylinder, and then I'm good to go. For the second one, same setup. 250 V1 equals 50 times 10. Divide by 250. Divide by 250. If you do that, V1 is going to give you 2 milliliters of crystal violet. So that means you're going to need 8 milliliters of H2O. Pause and think really quickly. How could I do that faster? Well, here the concentration is 25 micromolar. Then you need 1 milliliter of it. So if I want to go to 50 micromolar, that's twice as concentrated. So I would need twice as much crystal violet. 2 milliliters instead of 1. A quick way to check it. So last but not least, if I wanted to make a stock solution that was 100 micromolar, 250 times V1 equals 100 times 10. Divide both sides by 250. If you go ahead and do that, V1 you're going to get is going to be 4 milliliters of crystal violet, which means you would need 6 milliliters of H2O. So you want to feel comfortable with these dilution problems. You want to feel comfortable with Beer-Lambert's law, which basically, big idea, converts between absorbance and concentration. You want to understand what a cuvette is, how it works in a spectrophotometer, what it actually measures, absorbance. And then we're going to figure out what are X, what are Y, what is the rate constant by doing our own data and analyzing it.